Stop trusting small AI models, at least until you watch this. We've all seen it. A compact model gives you an answer with 100% confidence, but it's 100% wrong. This is the small AI dilemma. While massive LLMs can hide behind their scale, small language models are prone to factual blunders because their memory is strictly limited. But what if we could teach them to be humble? What if we could build an AI that actually knows when to stop talking and ask for help? Today, we're diving into the frontier of selective generation. We'll explore why standard loss metrics are blind to the type of error an AI makes, and why a typo is fine, but a factual lie is a deal breaker. By the end of this video, you'll understand the new framework for acceptability that is making small models smarter than ever. Let's get into it. You won't want to miss this.
All right, welcome back. Today, we're going to talk about something really interesting, a new way to think about making AI smarter. And it's not about stuffing it with more facts. No, it's about teaching it something we all value, knowing when to ask for help.
So yeah, it really all comes down to this one big question. I mean, think about it. In people, we really respect someone who can say, you know what? I don't know the answer to that. It's called intellectual humility. So the billion-dollar question is, how in the world do you build that into an AI?
All right, so let's get into it. The whole issue really kicks off with these things called small language models, or SLMs for short. Now, these guys are built to be super fast and efficient, but as you can probably guess, that speed and efficiency, well, it comes with a pretty big trade-off.
So you've got these two camps, right? On one side, you have the absolute behemoths, the large language models, the LLMs. They're trying to basically squeeze the entire internet, all of human knowledge, into their digital brains. But then you have these smaller, more compact SLMs, and their memory, it's way, way smaller. This means they're way more likely to make stuff up, what we call hallucinations. It's a huge problem.
And this quote from the researchers really just hits the nail on the head. They're super clear about this. These smaller models are not designed to be walking, talking encyclopedias. They're not meant to know every single fact about everything. Their whole purpose is to be nimble, to be fast, and, this is the key part, to understand what they don't know.
Okay, so that raises a pretty obvious question, right? If the AI isn't supposed to memorize everything, how does it decide what to learn and what to just let go? Well, the first big idea was to look for a sign, a kind of digital clue that the AI gives off when it's really struggling with a piece of information.
And that clue is a little something called loss. The best way to think about loss is as a surprisometer for the AI. So when it's training, if it gets an answer right and the loss is low, it's basically saying, yeah, no big deal, I saw that coming. But if the loss is high, that's the AI screaming, whoa, where did that come from? It means the correct answer was totally unexpected.
So the logic seemed really straightforward. If a certain fact always gives the little AI a high surprise score, a high loss, then that fact must just be too tough for it to remember. The solution? Simple. Just teach it. High loss means don't guess. Instead, ask for help from a bigger AI. Seems totally logical, right? Well, not so fast.
And this is where things get really, really interesting. Because that super simple, super logical idea, it has a massive flaw hiding just beneath the surface. And it's this. It turns out that not every surprise is actually a mistake.
You see, the researchers figured out that this loss metric, it's kind of blind. It can tell you that the model was surprised by an answer, but it has no idea why. It can't tell the difference between different kinds of errors, and that little detail, it changes absolutely everything.
Let's look at this example because it makes it crystal clear. Check out the top row. The truth is, Mozart was born in Salzburg. The AI predicts Vienna. That is a flat-out, 100% unacceptable factual error. And yeah, the loss is high. But now look at the bottom row. The original text said the cat. The AI predicted the time. Now, is that wrong? Not really. The cat and the time are both totally fine ways to start a sentence. It's not a factual error. It's just a different, perfectly acceptable choice. But here's the kicker. The loss, that surprisometer, can be just as high in both cases. The AI can't tell the difference.
So this brings us to a much smarter way to look at this, a new standard called acceptability. Basically, an answer is acceptable as long as it's still factually correct and makes sense, even if it's not a word-for-word match with the training data. This is the critical piece of the puzzle that just looking at loss was completely missing. Which, of course, brings us to the hero of our story, the solution the researchers came up with. It's a new training method they call Lassie. And yeah, it's a bit of a mouthful, but what it does is create a much smarter test for the AI.
And how it works is actually pretty brilliant. Instead of letting the small AI guess and potentially make a huge factual mistake, Lambdafy teaches it to do something else. It teaches it to output this special little flag, this call token. You can think of this as the AI literally raising its hand and saying, excuse me, I'm stuck. I need to phone a friend on this one. So how does it know when to raise its hand? This is the really clever part. LambdaC runs a simple two-part test. First, it does a grammar check. It asks, hey, is this word I'm trying to predict a fact? You know, like a person's name, a specific date, or a city. Then, and this is crucial, only if the answer is yes, it moves to step 2. It asks, okay, since this is a fact, is my surprise meter, my loss, really high? And if the answer to both of those questions is yes, that's when it knows to use the call token. Simple, but so effective.
It's a really smart idea on paper, for sure. But the big question is always the same. Does it actually work? Well, let's take a look at the data.
So in this first test, the AI's job was to write biographies. We're measuring something called fact score, basically how factually accurate are the biographies. You can see the baseline model, without any special training, is pretty dismal. Some other methods do a bit better, but then look at LambC. It's the clear winner, generating way more factually correct text.
Okay, this next chart is really cool. It measures something called fact leakage. And here, a lower number is actually better. What this is testing is, if we take away the AI's ability to call for help, how often does it still try to answer a tough factual question from its own tiny memory? And once again, look at LambC. It has the lowest score by far. This proves it really learned the lesson: don't try to be a hero and memorize facts you can't handle.
But this might be the most important part of all. It's about a huge practical advantage: money and resources. Just look at what it takes to get the training data ready. These other methods, they need these super expensive, power-hungry GPUs to work. We're talking about serious, expensive hardware. But LambC, its whole process is so darn efficient it can run on a regular old CPU core. I mean, this is an absolute game changer. It means you don't have to be a tech giant with $1 billion data center to use this smarter training. It makes it accessible to almost everyone.
All right, so let's step back for a second and think about the big picture here. Why is all of this, teaching an AI to know its limits, why is it such a big deal?
So, let's just recap the big takeaways. First, for these small AIs, trying to memorize everything is a surefire way to make them unreliable. Second, we learned that just using difficulty or loss as a guide doesn't work, because it's blind to what kind of mistake it's seeing. The real secret, the trick that Lassie figured out, is to combine 2 checks. 1, is this a fact? And 2, is it a hard fact? And putting those together gives us AIs that are not just smaller and cheaper, but way more trustworthy.
And that really leaves us with one final big idea to think about. We tend to define intelligence as knowing all the answers, right? But what if that's wrong? What if the most intelligent AI, and maybe the most intelligent people too, aren't the ones who know everything, but the ones who know exactly what they don't know, and have the wisdom to ask for help?